We will complete the steady state analysis of a forward converter in this part 3. In the previous parts, we have been considering the case where the number of reset turns is equal to the number of primary turns, and we saw that resulted in a Dmax of 0.5. In this part, we are going to relax that constraint and consider the case of arbitrary n primary to n reset and see its implication on the maximum duty ratio and therefore on the design of the forward converter itself. In addition, we will also look at two variations of the forward converter which have slightly different reset mechanisms. These are the equivalent circuits for the forward converter in the three distinct intervals. And when you consider the case where n primary to n reset is 1:1, then we analyze the waveforms in detail. In particular, the V primary during the on interval is Vn, and during the first off interval 1, it is negative Vn because the reset winding has voltage Vn applied across it through that reset diode. And since the turns ratio between these two windings is 1:1, V primary is exactly minus Vn. And the reset current through the reset winding of the reset diode during this off interval 1 is shown here, and this magnitude is exactly same as the peak of the magnetizing current in the primary winding. And this is a corresponding flex. During the on interval, the flex was due to the magnetizing current, and during the off interval, it is due to the reset current. Now, these waveforms correspond to the case of d less than 0.5, as can be clearly seen from this V primary waveform. The on interval DTS is obviously much lower, much less than 1/2 of the total period. So it is for d less than 0.5, you can clearly see that it is easy to realize the volt second balance, or the V primary average, is 0, because we can easily find an area with minus Vn equal to this area under this Vn. So the average is going to be 0. Now what happens when we begin to increase the D and actually go beyond D equals 0.5? And that is shown in this series of plots. But actually I will run the Plex simulation file for each of these cases. So this is my schematic of a forward converter. And what I'm going to do is, this is where I control the duty ratio in open loop. So I'm going to run this simulation for 3 values of D, actually 4 values of D, starting from 0.3, 0.4, 0.5, and 0.6, which actually results in a non-steady state. Okay, so these are the plots corresponding to D equals 0.3. Okay. So actually we are seeing 1, 2, 3, 4 switching periods, and this is the start of the cycle, and this interval here is DTS, and this voltage is actually Vn, this voltage is minus Vn, and right at this instant during the off interval, the volt second balance has been met. This area here is equal to this area, so V primary average becomes 0 at this instant, then the voltages become 0, then the next cycle, and so on. Okay. And the middle plot is that of the reset current, and it jumps, has a value equal to Im peak, then comes down to 0 right at this instant when the switch voltage, when the primary voltage goes back to 0. Then again jumps at the next cycle's off interval, and so on. The third plot is that of the flex in the core phi c, and it increases with the primary magnetizing current during the on interval and follows the current wave shape of the reset current during the off interval 1, then remains 0, and so on. Okay. So that is for D equals 0.3. Then the next plot, next set of plots correspond to D equals 0.4. I will slightly increase the duty ratio, and actually the lower plot here corresponds to the new case, and this dotted line is the previous case, D equals 0.3, and this dark brown or red is D equals 0.4. Okay, so you can see the on interval has slightly increased. The period is exactly the same in all the cases, and you can see it takes a slightly longer time to make the V primary equal to 0, but it is well before the start of the next cycle. So this is certainly a valid circuit. If you look at the reset current, comparing this dotted line, which was the D equals 0.3 case, versus this red solid line, the magnitude of I reset peak has increased. Okay. That's because we are applying the voltage during the on interval for a longer time. The magnetizing current is higher, therefore the starting value of I reset is also higher, and it takes longer duration to come to 0. The slope is same as before. It is always Vin over or minus Vin over L reset. So the slope is the same. Starting from a higher current, it takes longer to reach 0, but it does reach 0 before the start of the next cycle. So we are in steady state. And as before, this is a flex waveform, and once again it rises during the on interval, comes down and reaches 0 at this instant when I reset becomes 0. Okay. Next, let me consider the case of d equals 0.5. Okay, so that is this third waveform here, and the on interval is exactly 1/2 of the total period, or on interval equals off interval, and we just barely just about meet V primary average equals 0. This area here is exactly equal to this area, and the reset current again starts with the even higher magnitude, and it is able to reach 0 exactly at the beginning of the next cycle. Okay? So that is really the border of steady state operation, and there is also seen in the flex waveform. It reaches the peak at 1/2 of the switching period, and then it comes down at the same slope minus Vn over L reset and reaches 0 exactly at the beginning of the next cycle. Okay, so that is still valid steady state. Then I come to consider the last case where I made d equals 0.6, okay, and notice that all of these cases my n primary is equal to n reset, 1:1. So this is the case where the fourth case where d equals 0.6. So this is minus this Vn, this minus Vn, and I'm applying Vn for 60% of the total period, and I'm applying minus Vn only for 40%, the off interval of the 40% of the total period. Okay. So obviously this does not result in V primary average to be 0. The volt-second balance is violated. So it is not a valid operating condition in steady state. So in response, the reset winding current has a larger magnitude, of course, but it's not able to reach 0 before the end of that cycle or the beginning of the next cycle. And at this point in time, I turn on the MOSFET so to enter the next switching period. Okay. So starting with a higher value of magnetizing current, so I go to an even larger magnetizing current, even larger reset current, and it ends at even larger reset current, and so on. So you can see the reset current progressively increases without reaching any steady state, and this is even more clearly seen in the flex waveform. Okay, so again, this brown waveform, solid brown or red waveform, is the flex corresponding to d equals 0.6, and as you can see, the flex keeps increasing from cycle to the cycle to the next cycle, and that is a non-valid steady state circuit. Okay. So the point of this discussion is that for n primary to n reset equals 1:1, the Dmax is really 0.5. That is this blue waveform here. Anything more than that, we are unable to maintain volt-second balance. Therefore, the flex in the core keeps building. Okay, now coming back to the circuit, the forward converter topology. What happens when we make n primary to n reset to have any arbitrary relationship, not necessarily 1:1? So let's look at its influence on the V primary voltage. During the on interval, the voltage across the primary winding is still Vn, so it is Vn, and during the off interval, the reset winding is still connected to Vn. But what we are drawing here is the primary voltage, primary winding voltage, and its voltage is determined by the voltage applied to the reset winding and the turns ratio between the two. So it is no longer just minus Vn, it is minus Vn times the turns ratio. So we are looking at the primary voltage, so it's minus Vn times n primary over n reset. Okay. So that's the main difference, and by changing this ratio, we could have a larger or lower magnitude here, and therefore be able to have larger or lower Dmax than the previous case. The reset current is a similar wave shape. The main difference is that the peak of the reset current that happens right at the instant when MOSFET turns off is not simply the IM peak, but it is also scaled by the turns ratio. So the condition for flex continuity is that IM peak times N primary equals I reset peak times N reset. That gives the value of I reset at this instant. Okay. The flex waveform, again the concept or the equation of flex is exactly the same as before. And that is the Faraday's law relating the flex in the core to the applied primary voltage, and this is the peak value of the flex. So it's exactly same as the previous case where we had N primary to N reset to be 1:1. The only small difference that we can note is that in this case Dmax is not necessarily 0.5. It can be higher or lower depending on this new turns ratio. So let's go ahead and determine this new value of Dmax for an arbitrary N primary to N reset as shown here. Okay. So we drew the V primary waveform in the previous slide. It is Vn during the on interval and minus Vn times N primary over N reset during the off interval. Okay. Now I'm considering the operating condition which results in the border of valid versus invalid operation. That is, I'm operating at the maximum possible D value for a given N primary to N reset, and that is what this waveform corresponds to. Any value more than D, more than this Dmax would result in V primary average not being equal to 0, and any value of D less than this Dmax would result in a portion of the switching period where the primary voltage remains at 0. Okay. So this is a border case where the core reset happens exactly at the end of that particular period. Okay. So I call that as the Dmax. So this interval here is Dmax times Ts, and this smaller interval here, as drawn in this plot, is 1 minus Dmax times Ts. Okay. So let's apply the volt-second balance as applied to the primary winding voltage. So during the on interval, it is Vn duration of Dmax times Ts minus or it's actually plus the voltage during the off interval, which is minus Vn times N primary over N reset, times the duration, which is 1 minus Dmax times Ts, and that should be equal to 0 for steady state. Okay. So you can cancel out the Ts and the Vn in both of these terms, and what we have is Dmax over 1 minus Dmax is this turns ratio N primary over N reset. So once we have fixed this, then the Dmax is given by this expression, or once you know what the desirable Dmax is going to be, depending on the circuit design considerations, then we can go ahead and select the appropriate turns ratio between the primary and the reset winding, again using this expression. Okay, then the question is, how do you select the N reset or the ratio N primary to N reset? So the choice of N reset is really a trade-off. Lower values of N reset results in, from the equation that we just derived, results in higher Dmax. If N reset is lower, Dmax is higher. And high Dmax, it would mean that we know that, so if you recall, your VO is N times D times Vn, right? So if you increase Vn for a given Vn and given output voltage, you can reduce the N. So N secondary turns can be lower, and therefore the current reflected on the primary side, and therefore the MOSFET current, it will be N times IO. So lower value of N results in lower peak and therefore lower RMS current through the primary winding, and more importantly through the MOSFET, and that's a big advantage. And also we'll see when we look at the design of forward converter, which is actually identical to that of a buck converter, having larger D requires smaller value of inductance L for a given ripple requirement. Okay, so those are the advantages of having smaller value of L. But the disadvantage is that it leads to a higher switch voltage, or alternatively higher value of N reset results in lower switch voltage stress. So the expression for the switch voltage, V switch, so when this is turned off, this end is already at Vn, okay, same as input voltage, and the induced voltage here would be in this polarity, and that is equal to Vn times the N primary over N reset. So that is the voltage across the primary winding. That plus Vn is the total switch stress. So here if you make N reset larger, then at least this part of the switch stress equation is lower, and that results in lower voltage MOSFETs, which is again a big advantage. So it's really a trade-off. Usually if there is no other compelling reason, then choosing N primary is exactly equal to N reset. That is a very popular choice. It has a lot of practical advantages. I mentioned that we are going to look at two variations of the forward converter with slightly different reset mechanisms. So the first one is actually a fairly widely used variation called the two-switch forward converter, and the schematic is shown here. And here the two MOSFETs S1 and S2, they are turned on and turned off simultaneously, meaning they have the same gate signal. Okay? So during the on interval, when both the switches are on, the operation is identical to that of the basic forward converter. And when the two switches are turned off, the flex continuity is maintained by having the two diodes on the primary side conduct. When the two switches were conducting, the magnetizing current was entering the dot. Okay? And when the switches were turned off, just the magnetizing current component would continue to flow into the dot in this primary winding. Then S2 is turned off, so we'll find the path through the diode DR1, go up this direction, and enter the input DC voltage source, and then continue the path through the diode DR2, and then enter back this way. So the energy stored in the magnetizing inductance in the core is once again fed back into the source through the two reset diodes. Again, if you draw the waveform for V primary, on interval is Vn, and during the off interval there is no ratio between some reset winding and primary to be considered. During the off interval, because of the two diodes DR and R1 and R2 conduct, they connect the primary winding again to the input source, but in a negative direction. So this V primary during the off interval is minus Vn again. Okay? And therefore once again we get the case where Dmax is exactly equal to 0.5. An advantage of the two-switch forward converter is that even though you're using two MOSFETs, the voltage rating of each one of them is simply the input voltage maximum, Vn max. Okay? So that is because consider when S1 is off, so that is during the reset mechanism, we know that the diode DR1 is conducting, and DR2 as well. Both DR1 and DR2 are conducting. So if DR2 is conducting, then this end is tied to the ground. Therefore, the voltage across S1 is simply Vn, okay, Vn max. And we can also do a similar analysis for S2 and see that because DR1 is conducting, this end is connected to Vn, and this end is always at ground. So the maximum voltage across the switch is once again Vn. Okay, so the second variation is shown here. Just like the reset winding can be connected directly to the input source in the basic forward converter for reset mechanism, we can also connect, as shown in this figure, the reset winding directly to the load. So in the case of the basic forward converter, the energy stored in the magnetizing inductance was fed to the input source during the reset process, whereas in this circuit the energy stored will be fed directly to the load or the output stage during the reset process. Okay? So we need a current that enters the dot when the switch is turned off. So this diode, reset diode, supports a current that enters the dot. So current enters this reset winding, then completes a path through the load output stage, and then completes a path like this. Okay? So I'm now going to go through the analysis of this. It'll be a good exercise to actually determine what is the Dmax for this circuit. All you have to do is to draw the complete waveform of V primary. During the on interval, it is always Vn. Figure out what is the voltage during the off interval. Write the volt-second balance equation, and then that will give us the expression for Dmax. Similarly, once you know the V primary, you can also use that to calculate the switch voltage rating, which also I will leave it as an exercise.